Testing, testing. Okay, let's begin. Hello, this is our group project. The name is Fusion Learning for Test to Secret, a dynamic knowledge-based approach. And this is our group, 5 members, which are Hongming Yiheng, which is me, Xiao, Yalin, and Yingheng. Okay, here is the introduction to Test to Secret. Test to Secret is a critical task in natural language processing. The aiming to automatically convert natural language questions into executable SQL queries. This capability is essential for enabling non-technical users to interact with databases using natural language, thereby democratizing data access and reducing the barrier to database querying. So despite the significant advance in large language models, generating accurate SQL queries remain challenging due to, first, the complexity of database schemas with multiple tables and relations. Second, the need for precise understanding of domain-specific terminology. Third, the requirement to handle various SQL constructs, including joins, aggregations, and subqueries. The fourth, the diverse of natural language expressions that can present the same query intent. So here we give our methodology, a dynamic knowledge-based fusion learning test to circle agent. And there are mainly three components of our agent. The first is a test to SQL agent, which can generate SQL queries using an LLM. The second is dynamic fusion retriever, which can select relevant examples from the knowledge base. The third is the knowledge base manager, which maintains and updates a collection of successful examples. So there are two alternative dynamic fusion retrievers. First is a rule-based retriever, and it means focus on the database matching, keyword overlapping, query meta matching, and the semantic similarity to match two cases. The second is the embedding-based retrieval, which use the embedding model to calculate the similarity between the current question and each example, and use KNN approach to extract the top K cases. So the important point of our methodology is the self-learning mechanism. So at the initial stage, the system starts with an empty or minimal knowledge base, which means there might be no examples for future to use. The second, for each new query, the system retrieves relevant examples from the current knowledge base, if there is any, and generates a SQL query. And the third step is to validate the generated SQL by comparing it with the ground truth. And the fourth is if the generated SQL is equivalent to the ground truth, this example is added to the knowledge base. This represents the system learning from its own successful outputs. So the final step is the future queries benefit from the accumulated knowledge, as a retriever can select from a larger and more diverse set of examples. So the dataset we use in our experiment is the BERT dataset, which is a big bench for large-scale database grounded test-to SQLs. The metrics in our experiment, here we mainly use the equivalence rate, which is the proportion of samples where it generates SQL is equivalent to the ground truth. We also consider fill rate and the timeout rate. So there are totally three experiments focusing on different aspects. The first is the learning curve analysis experiment. The objective is to investigate how the equivalence rate exchange changes as the knowledge base grows incrementally. So here we see 10 epochs, where each epoch has 20 new training samples to the knowledge base. And each epoch we evaluate on a fixed test set of 100 samples. For the retrieval type, we use the embedding base, and the number of few shots is always 3. So let's see the results of the first experiment. From this data, we can see a positive learning trait in the knowledge base growing. As we can see, the equivalence rate grows a clear improvement trend starting at 35% in the early epochs and reaching 48% at the epoch 5, with the final epoch achieving 47%. This demonstrates then the embedding-based retrieval system benefits from a growing knowledge base. And then the second experiment is the few shot number comparison. So the objective is to determine the optimal number of future experiments to include in the prompt. So here we see different values of K's on a fixed test set using the knowledge base built from the full training set. So also the retrieval type is embedding base, and the knowledge base contains 88 successful examples. So from the result of the future number comparison, we can see the best performance is achieved with K equals 2 and 3, demonstrating that small number of highly relevant examples provides optimal performance. This confirms that embedding-based retrieval effectively identifies the most useful examples. Also, we see diminishing returns with large K. Performance decrease when K increase beyond 3. With K equals 10, achieve only 41%, which is the same as a 0 shot. This suggests that including too many examples might introduce noise and reduce the example's focus on the most relevant example. Here is experiment 3, the retrieval method comparison. The objective is to compare the effectiveness of different retrieval methods. Here we see 4 methods now, which is like do not use any few shot. The second is rule-based. The third is embedding-based, and the final is hybrid-based, which means first use the embedding-based and then use the rule-based to match cases. So the experiment result is very clear. The embedding-based retrieval method achieves the highest equivalent rate with 49%, significantly outperforms the other methods. This represents a substantial improvement of like 8% points over the baseline. So the discussion is about the limitation. The first is the dataset size. We only use 200 training samples and 100 training and testing samples. The dataset is relatively small. The results might not generalize to larger and more diverse datasets. The second is we only evaluate with GPT-4 mini, and different models might respond differently from future learnings. And finally, we only use execution-based equivalence checking. However, we did not use the efficiency, which means which can evaluate the quality of generated query. So finally, this is a conclusion of our project. In this work, we present a dynamic few-shot learning framework for test-to-sequel that implements an experience-based self-learning mechanism. Our system incrementally builds on the knowledge based from successful examples, enabling continuous improvement without model retraining. The first is there are some insights we get from this project. The first is embedding-based retrieval significantly outperforms other methods, achieve the equivalence rate of 45% compared to others. The second is the optimal number of future example is 2 or 3. And the third is the knowledge base growth shows positive learning traits, with equivalent rate improves from 35 to 48 as the knowledge base grows from 7 to 8 examples. And the fourth is future learning provides clear benefits with performance improved from double shot of the optimal future, but diminishing returns are observed from K to existing XA3. And finally, the self-learning through incremental knowledge-based construction with embedding-based retrieval is a valuable and effective approach for improving text-to-signal systems. That's all. Thank you.